Right, so those are some examples of naming different things. Finally, there's one additional thing. Can we name this one here? What's the name of this one? Yeah, this one, it turns out is copper fixed or variable? Variable. And so we need the charge on it, and you can figure out the charge based on this. We know that SO4 is -2, therefore it's got to be copper Roman numeral 2 sulfate. And so this is copper 2 sulfate. It turns out that when you buy copper 2 sulfate, there are two forms that you can purchase it in. The two forms that you can buy this in are this. You can buy anhydrous copper 2 sulfate. Anhydrous, do you know what that means?
No.
Anhydrous is without water or no water. And so it's just CuSO4. And so sometimes we'll call this anhydrous copper 2 sulfate because when you look in the chemical catalog, you can buy another one too. The other one that you can buy looks like this. It's going to be CuSO4.5H2O. Both of these are solid. This is copper 2 sulfate. That's we have to call this something else. This is the hydrated form, and it doesn't look wet with water. You know, it looks solid. And what would we call it? Well, what we call this is copper 2 sulfate pentahydrate, or 5-hydrate. And so what are these hydrate? These are, the waters end up being waters of crystallization or hydration. The water molecules that are included as structural parts of the crystal formed from water solution. It doesn't even have to form from water solutions. It's like, some crystals pick up water from the air. And so what happens is if a water molecule, and there's humidity here, the relative humidity today, the air is not totally dry. There's some water vapor in there. And if that water vapor strikes the crystal, sometimes it's stuck on the crystal because of the stickiness of the crystal and the water. So it gets stuck. And so what does that look like? Let's take a look at the two forms of copper 2 sulfate. And so if we just do a search, CuSO4, we're going to see this in the images here. All right, on the left is anhydrous copper 2 sulfate. It looks pretty dry, right? On the right, these crystals aren't wet, but they kind of look wet. This is the hydrate, the 5-hydrate. And so what happens is the waters, they not only get stuck on the surface, the waters can wiggle their way into the crystal structure itself. And so when we look at the crystal structure of copper 2 sulfate, let's take a look at that copper sulfate. I'm just going to call it copper sulfate crystal structure. And then see how things are packed together in the crystal itself. Is this it? Yeah, this is it. So this is, it's showing how things are connected or interconnected. Usually we connect these with the nearest neighbors and that kind of stuff. But what happens is the water molecules can get stuck on outer surface, but when they get stuck on the outer surface, they can also creep into the crystal lattice itself in these what we call void spaces, little gaps here. Water molecules are small, and so it turns out these kind of act like a sponge. And the maximum number of waters will be 5. We can put fewer than 5, it won't be saturated sponge, but partially saturated sponge. And so, but 5 is the max. And so you squeeze in 5 water molecules per formula unit of copper 2 sulfate. So for every copper and sulfate, we can get 5 water molecules. We got a lot of copper sulfate formula units. We're going to fit a lot of water molecules in there in this ratio. And so this is a hydrate. This would be the pentahydrate or the 5-hydrate. Actually, you can switch between one or the other. It's easy to form the anhydrous form. The anhydrous form, all you do is dry it in an oven. So if you dry this in an oven, what happens is you heat this up, it's going to drive all the water molecules that are stuck in the voids out of the crystals, leave you with an anhydrous form over here. So it's pretty easy to do. Dehydrate the crystals. And to rehydrate the crystals, you just let it sit in air. We don't add water to the crystals here. You let them sit in humid air, and eventually they'll rehydrate this. In fact, some crystals are used to desiccate the air. Have you ever heard the word desiccate? Desiccate just means dry out. And so if you leave a whole bunch of these crystals out on the countertop, the humidity in this room is going to go down because the crystals are going to suck the moisture out of the air, basically. In fact, we buy desiccants. Copper 2 sulfate would be an expensive desiccant. There's much cheaper desiccants that we can buy. And the desiccants, you can buy them in little packs like this, desiccant packs, cheap ones. And you put them in little things like drug bottles or whatever else that you don't want any moisture in. This will just suck the moisture out of the air and incorporate the waters into a crystal structure. Probably the most common desiccant is, what is the most common desiccant? Let's see, this has to have an MSDS form. Let's see what the active ingredient of this is. It's the SDS form, it's a safety data sheet. Substance name, desiccant. I wonder what element or compound that is. Substance name, desiccant. Wow, this is not very informative. This is not very informative. I guess it must be a trade secret. But let me tell you what one of the most common desiccants is that people use. If you buy it from a chemical company, let's say Tyvek bag desiccant, would be like calcium sulfate. Silica gel is also a common desiccant. Calcium chloride, calcium sulfate. I used to use calcium sulfate all the time. They call it dryerite. But the problem with dryerite is it doesn't change color. Anhydrous calcium sulfate looks like this. The hydrated form looks like this, right? And so they look the same. And so what they do, this goes by the trade name dryerite. When you buy dryerite, what they do is they put a dye in there. And the dye changes color. So if the dye turns red, it's saturated. If the dye is blue, it's good. So when this turns red, you just recycle it. You just throw it in the oven until it turns blue and then reuse it. That's dryerite. And we use it in something called a desiccator. You see, is that good dryerite or bad dryerite? That's good dryerite. Anhydrous calcium sulfate. Let's see if we can see some bad dryerite. If they have some shots of bad dryerite here. blue, blue, blue. Do you see this one over here? That's bad. Blue, blue. This is white, you can't tell the difference. This is anhydrous, this is hydrated. So heat it up, hydrated. There's lots. And then we usually place those in something called a desiccator. A desiccator could just be a closed bottle, you know, like your drug bottle. But we use fancy desiccators like this. They're expensive. Well, that's pretty cheap, $29.20. Cheap compared to this, $124. Difference. Yeah, that's really cheap for desiccator. You know, if you break our desiccator, they're going to charge you like a lot more, like $53 or something. But nobody's really broken it. People have chipped the lid. It's made out of glass. They've never charged anybody. A lot of people use plastic ones like this. But, you put your desk in there, and you can dry out whatever you're trying to dry out. All right, so that is the hydrate. Here. And so let's answer these questions here. How many water molecules are associated with each formula unit of anhydrous sodium carbonate? And so anhydrous sodium carbonate has no water stuck in the lattice. And so when we look at this is sodium carbonate. How many water molecules? 10. 10 per formula unit. Formula unit would be 2 sodium ions, 1 carbonate ion. Name the hydrate. Okay, so what's the name of that? So sodium, fixed charge or variable charge? Okay, so it'd just be sodium, name of the anion, carbonate. So sodium carbonate, 10 is decahydrate. So this would be sodium carbonate decahydrate or sodium carbonate 10 hydrate. I don't know why there's a shift away from the prefixes. So let's see what they're going to do, deca or 10. They did deca. Sodium carbonate decahydrate, 3 words. Write the formula of nickel 2 chloride hexahydrate. Can you write the formula for nickel 2 chloride hexahydrate? Get it? What did you get? NiCl2 dot NiCl2 dot 6H2O. Good. All right, here's a little summary of the nomenclature system. I didn't follow. You know, your book's way of remembering this and memorizing this is different than mine. You could use either way, I don't care. And so I'm not even going to bother going through this summary here, because they have a totally different system than my system. What time is it now? 3:24. All right. So that's chapter 6. So we're going to have some memorization to do here. What is chapter 7? Let me just take a peek. Chemical formula relationships. Get that later, but we have a lab on Thursday. It's nomenclature, and it's going to be exercise A in your lab supplement. Exercise A, though, has two parts. One part is nomenclature, the other part is quantum mechanics, but we haven't gotten to quantum mechanics yet, so we're just going to stick with the nomenclature. And so we'll do some more examples of nomenclature. Since I'm out of sync with the morning class, I have a little bit of time to do a couple of things. One is, were there any questions for the homework? No? Okay. I'm sorry? Was there a question or? For chapter 6? Not yet. I got to give you homework for that. But you should know, what were the two major reference books for chemists? Two major reference books. Let me ask you that. Print books. You recall what they're in? The Merck Index. So I just wanted to show the Merck Index. This is the Merck Index here. This is an old edition, the 7th edition, the Merck Index. Merck Index. This, I think this school got it used. I'll show it to you here. I want to just show you what it looks like. That's what it looks like, the Merck Index, 7th edition. This is the one we have in the lab stockroom. Index. Periodic chart of the elements. Looks like they picked it up for $12 used. $12. Merck Index. Merck Index of Chemicals and Drugs, an encyclopedia for chemists, pharmacists, physicians, and members of the allied professions. This is a preface. And if we look at the table of contents, periodic table, atomic weight, usage, abbreviations, chemicals and drugs. Chemicals and drugs takes up the bulk of it. If you look at chemicals and drugs, it goes from page 1 to page 1121. And then there's some other chapters, cross-index of names, because we have so many different names, common names, etc. So cross-index. Organic name reactions, so certain types of famous reactions named after people. Table of radioactive isotopes. Radioactive isotopes used in medical therapy and diagnosis, first aid and poisoning, calories in food, biological units, Greek alphabet, Russian alphabet, alchemical symbols used in biology and botany, Roman numerals, metric system, U.S., British, and metric, conversions, boiling, melting, etc. There's a lot of data there in here. And so let's take a look at like a typical entry. We can find different entries here. Let's find something here. Merck Index has not only compounds, but it also has mixtures. So let's look at a mixture here first, really quick. LMNO. One mixture might be oil of pine needles. Obviously, that's not going to be a compound or an element, or just different names. So oil of pine needle also goes by oil of Scotch fir, also goes by firwood oil, volatile oil from this. And what are the constituents? Different constituents. We want to know if we have oil of pine needles, we want to know what about the composition, the percent composition by components. Here they're giving us the density and some optical property. They're telling us this is medicinal use. See oil of dwarf pine needles. We go to oil of dwarf pine needles, and maybe there's some additional. Oil of rosemary, oil of spearmint, oil of thyme, oil turpentine, oil spike, etc. And then we also have, organic and what we call inorganic, like minerals. Mineral is olivine. Olivine is magnesium, iron, silicate. This is a compound here. Minerals are compounds. Some minerals are elements, like gold. And then here's another mixture, olive oil. Is olive oil a compound, substance, element, mixture? Olive oil. I'm just curious, what are the constituents of olive oil? I want to know the composition. So it's 83.5% oleic acid, 9.4% palmitic acid, 4% linoleic acid, and stearic acid at 2%, racitic acid or acetic acid 0.9%, and then there's minor constituents of 0.7%. So that's it. However, if we're looking at, that composition is not going to be fixed because, mixtures don't have fixed composition, so that's, your typical composition. However, if you're looking at a substance, let's pick out a substance here. For example, we'll pick out the substance phenol down here. Phenol is the common name, of this. Is this a binary molecular compound? And it's C6H6O. That's phenol. No, it's not. It's trinary molecular compound. It's molecular because it's all non-metals. However, did we come up with the nomenclature rules for trinary molecular compounds? No. And so what do we do with trinary molecular compounds? Nothing. We just unless they fall under some other set of rules, we aren't going to do anything with those. It could be an acid, like nitric acid, and then we know, but this one we don't. But phenol also goes by the name, carbolic, phenic, phenolic acid, phenyl hydroxide, hydroxybenzene, oxybenzene. Those are all different names for phenol. And so it just goes through, other names here. And then it gives us the formula. This is a substance. So a substance is going to have a fixed composition. The fixed composition in terms of this is going to be 6 atoms of carbon, 5 atoms of hydrogen, 1 oxygen, 1 more atom of hydrogen. And then it gives us the what we call the molecular weight. The molecular weight is the average weight of the molecule. Some molecules are going to be heavier, some molecules are going to be lighter, depending on what isotopes we have. So this is the average weight of a single molecule of this. This is the formula rewritten differently. We have a total of 6. But when we look at the carbons, it's going to be 76.57% by mass carbon, 6.43% by mass hydrogen, and 17% by mass oxygen. Where it's obtained from coal tar, fusing soda, benzene, etc. And then it goes on. Phenol turns out to be a pretty common chemical here. And so it gives us the structure of phenol. It gives us the crystal structure here. There's some reference here. It tells us some of the physical properties. Physical properties, colorless, the type of crystal it is, the color of the crystal is, prone to redden on exposure to air and light, hastened by presence of alkalinity. So it gives us a little bit about the chemical properties as well, physical and chemical properties. Again, this is incompatibilities. These are more chemical properties here. Uses. Used as a general disinfectant, phenol. Mixed with slate lime, etc. for toilets, stables, cesspools, floors, drains, etc. Medical uses and dose. Topically as an anesthetic, etc. Toxicity, veterinary uses. Here. Etc. And so the Merck index has more of a biology spin to it, whereas the CRC, do you recall the CRC? This is the other book I mentioned, the CRC Handbook of Chemistry and Physics. This has more of a physics twist to it. And so when we look at the compounds here, there are a lot of compounds here. And they don't get into them in as much detail. So let's pick up, for example, phenol in this book we could do as well. So let's see, phenol. Here we go. Phenol, aka carbolic acid, benzene, hydroxybenzene. This is the average weight of a molecule in U, 94.11. Some other properties there, including melting point, boiling point, solubility, etc. And that's it. You know, but the thing is, the CRC has way more compounds than the Merck index does. The CRC also has a lot of physics type stuff. So, for example, the Merck index has no table of isotopes, whereas the CRC has a gigantic table of isotopes here. So those are two common reference books that we use. And so what I want to do, though, is I want to give a little quiz just to see where you guys are at with the isotopes. Yeah. That's a big hint there. This is open notes. This is an open book. Open it up. The quiz is going to be for this carbon monoxide. The question is, like, obviously carbon monoxide has a lot of chemical properties and other things, but when we think about this carbon monoxide itself in, let's say, polluted air, or if your burner isn't burning efficiently, you might form some carbon monoxide. If you form carbon monoxide, then that means there's not enough oxygen. We want more oxygen to form carbon dioxide. But is there a risk of adding too much oxygen such that we form carbon trioxide? Did I talk about carbon trioxide? Yeah. Will we see any carbon trioxide? No. And so what we say is that carbon dioxide is what we get from complete combustion. But let's go ahead and do this at carbon monoxide. We're going to leave it at carbon monoxide because it's a little bit easier. That is, if we did generate some carbon monoxide, how many different carbon monoxide molecules exist? Are all the carbon monoxide molecules in air identical? No. How many different carbon monoxide molecules are there in air? And so you'll need some data The data you can find in something like the Merck Index or online. If you go online and do a search, and what you're going to find is that most of the tables online are abridged. You know, they're not very complete. Whereas the Merck Index, I mean, not the Merck, but the CRC tries to have the most comprehensive table available at any one time. So let's take a look at this table here. This is from Shaka's lab. You know, chemically, the carbon monoxide molecules are all going to behave pretty much the same. In fact, the same. There are some slight differences, but in terms of chemical reactivity, they behave the same. You know, no matter what carbon monoxide molecule you form, you want to burn it completely to CO2. CO2 is a lot less toxic than CO. The question is, how many CO molecules can be found in air, polluted air? Hopefully, when we go outside, there's going to be some carbon monoxide because cars are going to emit small amounts of carbon monoxide. How many carbon monoxide molecules can be found in air? What are they? Let me know when somebody has the answer.